Hi, welcome. This lecture is something special. In this, I am going to give a summary of the Cauchy theory, how it developed. Essentially, I am going to look at various major steps or landmarks or milestones which culminated in the two major results of Cauchy, namely existence of primitives, local primitives, and a function is holomorphic if and only if it's analytic on an open set, right? So these are the results. And the reason why I say that is usually in complex analysis, many of the courses become essentially complex calculus courses rather than analysis. For example, I will be very surprised whatever you did about Cauchy's theorem, okay, this kind of sequel, whether it has been digested, understood by many who went through such a course. Okay, but if you want to be a professional mathematician, I think it's important that you should have this, okay, how the theory developed, so that you have an idea. Okay, so it's like standing on the top of a hill and looking down the town below, so that you get how the layout of the city. This is what you want to do. Okay, and second thing, and it's something very important, I will deviate from my usual style. Okay, because many of you had complained about my handwriting, but this summary I want you to understand thoroughly, so I'm going to give presentation mode. Okay, I hope we will succeed. Let us see. Okay, so this is Cauchy theory, a summary. Okay, my course is based on my book on a pathway to complex analysis, so I am going to give references to theorems with their numbers in this presentation. Okay, so I don't have any other reference as far as this particular thing is concerned. Now, many of you wanted to know how to buy a copy of my book, so here are the details. You can either write to technoworldpublishers@gmail.com and tell them what book you want to buy, what is the cost, how to pay for it, and is there any postage charges, how much you have to pay for it, and how to pay for it, like Google Pay or Paytm or bank transfer or money order, whatever it is. Okay, and you can also call Techno World Publishers on this number. Okay, keeping it on so that you can note down. If nothing else works, you can talk to one of the persons, Mr. Akibur Malik, on this particular number. Please take down the number if you want. Okay, so what is Cauchy theory about? As I have been saying, there are two major results of Cauchy on the theory of holomorphic function. Okay, what is it? There will be still spelling mistake, as we can see. F is holomorphic function on open set in C. There exists another holomorphic function G on U such that G dash equal to F. That is what is called the existence of a primitive. Okay, and this is not exactly correct. You have to put extra condition. Okay, so I should say it is local primitive. Okay, and for example, if it's a holomorphic function on a star-shaped open set, I can say it's a primitive. So this I should say local primitive. Okay, right. And the second thing, if F is holomorphic on a star-shaped open set and gamma is a closed path, then the path integral of F over gamma is 0. Okay, right. Notice that this will be somewhat easier. Why? Because if you assume the first one, okay, suppose I assume F is holomorphic on a star-shaped open set in C, then I know there is a primitive G dash. And if you remember our path integrals, then you know that if it admits a primitive, then the path integral of such a function over a closed path is 0. Okay, so Cauchy's theorem will be more or less immediate consequence of the first one, and please remember, I have to assume this is a star shaped open set in the first one. Okay, so that's why this second one, as I said, is a immediate consequence of the first one. And what is the second major result? Second major result is any holomorphic function on an open set, there is no condition on geometry of the set. It's just an open set, only topological condition. If it's an open set, then it is analytic. What does that mean? It admits a locally a power series. A function f is locally a power series. That means given any a, I can find an open disk bar contained in U such that f of z equal to the power series cn z minus a to the power n as n runs from 0 to infinity. This is for all z again in bar, not u. See, these are the mistakes. Okay, and one has to correct in the next thing. Okay, so these are the major results. So what is this lecture about? The path taken to prove the results of Cauchy is very labyrinthine. Okay, I don't remember the Hindi word for that. Okay, and the argument are what one may call as a bootstrap argument. That is, you look at the way uh, you tie a shoelace. You start from this, and another one goes from here. Then this goes from this, and this goes this, like that. So finally, you tie it up. So if you look at the Cauchy theory, okay, the way it developed is something like this. That is why it's a bootstrap argument. So often the beginners miss the wood for the trees because you are bothered about too much of intricate proofs, etc., and you lose your way. Except if there is a guide like your teacher, he starts from here and reaches, namely that, but you will not know the way, how you went through the labyrinthine path to get out of that. Okay, you started the entrance, you got out the exit, but you may not know the way. Right? So this is what we want to plan to do. Now, what are the basic facts we need? Okay, these are two basic results on path integrals. What are they? This is the theorem 6.2.17 and its corollary 6.2.19. This is what I call fundamental theorem of path integrals. Suppose f from u to c is continuous. Okay, assume there exists a primitive, that is a function g from u to c differentiable such that g dash equal to f. Okay, then such a g is called a primitive of f. Then the line integral of f along any path in u depends only on the endpoints. So in particular, it's a closed path. Okay, then it has to be 0 because the endpoints turn out to be the same. Okay, and it is going to be difference of the function of the endpoints. Difference. Okay, it is going to be g of gamma b minus g of gamma a, but if gamma b equal to gamma a, then it is going to be 0. Okay, these are the only things. This motivates us. Look at that. What was the first result we wanted to prove? We wanted to prove if it's an open star shaped set and f is a holomorphic function. Okay, I wanted to say there exists a primitive. Okay, that was the first one. So how do I get it? This is the next result. Okay, look at this. This is theorem 7.1.3. So how do I know it as a primitive? That's this theorem. This is theorem 7.1.3. All these things I proved in my lectures, video lectures. Suppose u is open and star shaped, and suppose f is a continuous function. If I know the path integral of f over the boundary of t of any triangle, remember for me triangle is a solid triangle. The interior of the triangle, the bound is also included, that should be subset of u. So if the path integral of f over the boundary t is 0, then f is a primitive. Okay, please understand now, don't worry about the proof, go back. So what did I want to prove? Cauchy's first theorem said that if f is holomorphic, then it has a primitive. right? Now this, if f is holomorphic, it's differentiable, therefore it's continuous. Therefore I want to show it's a primitive. If I want to show it as a primitive, what should I do? Theorem 7.1.3 tells me what to do. I have to prove the path interval f over t is 0 whenever the triangle delta is contained in U. Yeah? So let us go back. So that is what Cauchy-Goursat says. That is theorem 7.1.8. What does it say? Let U be any open set. Assume f is holomorphic, then the path interval of f over the boundary t of any triangle is 0. Right? Now go back to the earlier result. Okay, therefore f is holomorphic, therefore is continuous, and path interval over the boundary of t is always 0. Right? You understand? Cauchy-Goursat says almost, but then in the last theorem, go back, I wanted U to be star shaped. If I want to say it as a primitive, then I have to assume it is star shaped. You follow that? So that condition if I put, then I will get the result. So now I got the Cauchy's theorem. Okay, now assume my U is open as well as star shaped. Okay, then let's look at 7.1.8. Then path interval of f over the boundary t of any triangle is 0. So this is in view of the last theorem which I said about path integral. Okay, this f must have a primitive. Yeah, using theorem 7.1.3, I know it must have a primitive. Yeah. So once it has a primitive, okay. Now go back to the thing, fundamental theorem of path integrals. It says the integral of such a function over any closed path in U must be 0 because it is a primitive. We follow that? Okay. So as I said, the first theorem, I said I should have said any holomorphic function has local primitives. Okay, so how will it follow? Suppose f is holomorphic an open set, give me any point. Okay, then there exists an open disk containing that point, which is contained in U. Okay, now U is convex. That open disk is convex, therefore star shaped. Therefore, f has a primitive on that particular disk. Therefore, f has local primitives. These are all easy ones. Yeah. Now, so the first thing we have proved. Okay, two are the major results. The first major result is the existence of local primitives that we have proved now. Now, what remains? What remains is analyticity. That is, any holomorphic function is locally a power series. That is the second major result which you have to prove. For that, what we need is the Cauchy-Goursat. What we did, that's okay. We want to slightly extend it, weaken the hypothesis. In the original version, what we need was f from U to C is holomorphic. Okay, right, and the triangle delta is contained in U. Then the path interval of over the boundary is 0. Right. Now, the way we are relaxing the condition is we will assume f from U to C is continuous, but it's holomorphic except at one point. That's good enough, right? But f is from U to C is continuous, perhaps, and it's also differentiable on all of U except at one point. Okay, then the conclusion of Cauchy-Goursat remains. That is, if I take a triangle delta which is contained in U, then the path interval of f or the boundary t will be 0. Okay, this is the extension. So once I have the extension, now again I have extension of Cauchy's theorem. What does it say? Let U be again star shaped and open. F is continuous and holomorphic on U except at one point. Okay, right? By extension of Cauchy-Goursat, I know that the path interval f over any boundary t of the triangle delta is 0. Therefore, by the theorem which I said 7.1.3 or whatever it is, okay, if the domain is star shaped, it admits a primitive. Once it has a primitive, interval of f over any path, closed path is 0. You follow that? Yeah? Right. So, now the next thing is This now how do I prove analyticity? Okay, the basic trick is again I have done it when we dealt with differentiation Cauchy type integrals. Okay, before that we will do that. Suppose you use star shaped and f is holomorphic, and suppose gamma is a closed path, and take a point A not on the path. Now look at the thing, Cauchy theorem to g of z equal to f of z minus f of z naught by z minus z naught for z not equal to z naught, and g of z naught equal to f dash of z naught. Okay, I didn't want to write all those things because it's a little too cramped. Okay, okay, this is for z not equal to z naught. At z naught it is f dash of z naught. Okay, then g is continuous on all of u and holomorphic except at the point z naught, right? Therefore I can apply the Cauchy theorem, extended Cauchy theorem. Take any closed path, then integral of g over the closed path is 0. But on the closed path, g of z is given by this formula, because z naught is not on gamma, right? Therefore, what do I get? Okay, using the linearity of the integral, I get this equal to this. Okay, so segregate everything, you get it. Okay, now what is this? If I know what this is, okay, this is for any gamma, I have to look at the path integral, right? So the easiest case is we had already seen this kind of integral dw by w minus a over a circular path. If the circular path with the standard parameterization, okay, that is a circular path is gamma t equal to a plus r e power I t. Okay, then I know this is nothing other than 2 pi I. Therefore 2 pi I cancels, right? Therefore I will have f of z, okay, that is f of a equal to this. This is for every z there, right? So I got Cauchy integral formula, right? Now that is the important thing. Now we look to a very general result which I proved in the differentiation videos. This is theorem 6.4.7 in my book. This is Cauchy type integral. Let gamma be any path and f is defined only on the track of gamma. Okay, f from track of gamma to c, let it be continuous. Then I can define a function g, okay, on c okay, minus this full stop should be outside, c the complement of the track of gamma by a Cauchy type integral g of z equal to f of w by w minus z for z not in here. Then what we proved was g is actually analytic, and in the end derivatives f of w by w minus z to the power n plus 1. This we have proved in our video, and this is also proved in theorem 6.4.7. Now let's go back to earlier result. Look at this. This says f of z equal to this. Therefore, okay, notice that now f is holomorphic. Okay, therefore I can define g of z equal to 1 by 2 pi a f of w by w minus z wherever z is not on the boundary of gamma, right? That is on the circle, right? Then I know g is holomorphic. Yeah, right. Sorry, analytic. G is analytic except when the complement, sorry, on the complement of the circle gamma, right? Now how did I get this? I got this here, therefore, okay, if z is outside gamma and that is mod z minus a is strictly greater than r, then I know this path integral we had already computed to be 0. Therefore that function g of z will be 0 if mod z minus a is greater than 0. But g of z coincides with the f of z. That's what Cauchy integral formula tells you. Since g is analytic, but g equal to f inside the open disk bz not r, then f is analytic. Therefore any holomorphic function on an open set is analytic. Okay, Cauchy integral formula for the derivative is the immediate consequence of this, as we have seen. Because now go back in this. So nth derivative of f will be 1 by 2 pi n. There will be an n factorial and f of w by w minus z to the power n plus 1. That's what this theorem says. Okay, that's it. I think I completed. So I hope this gives you an idea. Please go through it, and with this, okay, try to see, accept some of the things. Most of the things are now easy. The only thing is, as I said, it's a zigzag fashion. It goes here, something goes here, something goes here, something goes here. It's exactly okay tying a shoelace. Okay, and bootstrap argument. So that is the only tricky part. Now, once you keep this in mind, once or twice in your mind, then it will be very crystal clear how the theory developed. I hope all of you enjoyed. Okay. Unfortunately, this may not help you score high grades in your exams, but this will help you enjoy mathematics. Okay. Take care. Stay safe. We'll meet again.